So now in this part of the class, we're starting to move into the section about how Earth's climate has changed through deep geologic time. And so we're going to have to introduce, some new ideas of how scientists study climate, right? What are the techniques that we use to try and understand something that happened so long ago? So we introduce this idea of climate proxies. Now, a proxy is some sort of physical record that serves as a substitution for a direct measurement. And there are many different kinds of climate proxies. To illustrate one of them, here we've got a paleogeographic map of the Earth's surface about 90 million years ago. And so you can start to see it resembling the Earth that we know today. Here's North America, Florida is sort of outlined here, though it's probably underwater at this time. The Gulf of Mexico is starting to form. Most of North America, as you can see, is sort of flooded, right? Sea level is very high at this time. But you can see that Africa and South America are starting to break up. Australia is drifting away from Antarctica here. India is sort of out in the middle of the ocean, right? So familiar elements, although the distribution of all these different continents is very different at this time. But one of the unique things that we see at this time in Earth history, about 90 million years ago, is if we go back to the rocks that were at the north and south poles, right? So Antarctica is pretty much where it is today at this time, or it hasn't moved a lot since then, and North America is the same. But so if we go to the rocks of northern Canada that are about 90 million years old, and we look at the fossil record of these rocks, we see something very interesting. Now, usually when we think of fossils, we think of dinosaurs, but there's also a very rich plant fossil record throughout the world. And so this is a figure from the textbook that we're using of a fossil breadfruit tree leaf from northern Canada that's about 100 million years old. And so basically this leaf here, the shape of this leaf, resembles plants that grow in more tropical climates today, right? If you look at the plants in northern Canada today, you have no plants that look like this. None of these broadleaf tree kind of plants, right? They're all sort of mosses and kind of scrub bushes that you picture when you think of the tundra, right? Sort of barren, like flat plains of mostly moss and that sort of thing. So these kinds of plants only grow in warm tropical climates on Earth today, and yet they're found in places that were at the poles 90 million years ago, like northern Canada and Antarctica. There's also a rich fossil plant record in Antarctica that shows things like ferns and sort of palm tree-like plants at the north and south poles. So the geologic record has like fossils in it of, for instance, these fossil plants found in northern Canada, places that would have been near the North Pole 90 million years ago, as well as fossil animals that we know sort of can't survive in cold temperatures. Things like turtles that are cold-blooded, that simply can't survive in current polar regions. So these two lines of fossil evidence are a form of climate proxy, right? So they're not a direct measurement of what we think the temperature in the northern polar regions would have been 90 million years ago, but they tell us qualitatively, right, like descriptively, conceptually, that the conditions near the North Pole must have been warmer than they are today if plants that have broad leaves could live there, and animals like turtles could live there, right? So that's a form of climate proxy that is sort of qualitative. And so it's lines of evidence like that lead to this paleogeographic map being drawn the way it is, where you'll notice that there's no ice shown in Antarctica or in the northern parts, like northern Canada and Russia. There's no ice depicted on this map, in part because of the qualitative fossil record that tells us that cold-blooded creatures and sort of tropical plants must have been growing in these regions at this time. So that tells us that the climate of Earth 90 million years ago was very different than the Earth that we have today, right? It was warm enough to support tropical plants and turtles in the polar regions. Scientists also have more complicated and quantitative climate proxies that we use through time to understand Earth's climate. One of the most important climate proxy records that we're going to talk about in this part of the class is depicted here, and it's the oxygen isotope composition of benthic foraminifera. Okay, what the hell is that? So oxygen, we may recall, is an element, right? It's one of the most important elements in the periodic table, super important for life on Earth. An isotope, if you recall, we discussed this in the first part of the class. An isotope is an atom of an element that has the same number of protons in its nucleus, but a variable number of neutrons in its nucleus. And then benthic foraminifera. Benthic means something that dwells on the bottom of the sea floor, and foraminifera is the name of these organisms. They are single-celled organisms that live at the bottom of the ocean, benthic foraminifera. And the oxygen isotope composition of these tiny little shells that benthic foraminifera grow is a super important climate proxy through time. This climate record is also the focus of your lab exercise this week, and so we'll spend some time going through this diagram and describing it in complete detail, as well as talking about the different systematics of oxygen isotopes. So we're going to spend a lot of time thinking about how this plot works and what it's telling us. The first thing to notice about this plot is on the x-axis, we have time in millions of years ago, starting at 0 here, going back to about 65 or 66 million years ago. On the y-axis, we have delta 18O expressed in a per mil ratio. So we'll explore what exactly that means in greater detail. But basically, this is the oxygen isotope composition of these foraminifera through time. So if we think back to the beginning of the semester, talking about the periodic table, this list of all the elements in the universe, we can find oxygen right here. We see that its atomic number is 8. So that means that the definition of oxygen is any atom that has 8 protons in it. So if all oxygen has 8 protons, then there are 2 isotopes of oxygen that we're interested in. And those 2 isotopes are oxygen 16, which is denoted like this with the subscript 16 out in front of O for oxygen, and oxygen 18. And so oxygen 16, by definition, if it's oxygen, it must have 8 protons in its nucleus, 1, 2, 3, 4, 5, 6, 7, 8. And then it also has 8 neutrons in its nucleus, right? Particles that have no charge, whereas protons have a positive charge. Now, together, 8 and 8 is a total mass of 16, so the atomic mass total atomic mass equals 16, hence its name, oxygen 16. Same for oxygen 18. Oxygen 18 has 8 protons in its nucleus, because all oxygen has 8 protons, but 10 neutrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's got 2 extra neutrons for a total atomic mass of 18. So oxygen 18 is physically heavier, bigger than oxygen 16. It has an atomic mass that is greater than that of oxygen 16 by exactly 2 atomic mass units. So on this figure, showing the oxygen isotope composition of benthic foraminifera from about 66 million years ago to the present, the y-axis is showing the oxygen isotope composition of the shells of benthic forams. So this is a value that's shown here. It's expressed sort of 0, 1, 2, 3, 4, right, as this whole number. But we know that there's two isotopes of oxygen that we're talking about here. So how does this value, delta 18O per mil, how does that tell us about those two oxygen isotopes? Okay, so here we'll explain what this notation, delta 18O, is and why scientists use it. So it looks intimidating, but it's really not that bad. So delta 18O, so this is the Greek symbol delta, this kind of goofy squiggly guy here. Again, 18 for 18 oxygen, O, and then this per mil symbol here. Now what this value is the difference between the ratio of oxygen 18 to oxygen 16 that's measured in a foram shell as it's compared to a standard value that all scientists all over the world agree upon. Okay, so you take the individual ratio of oxygen 18 to 16 from a single foram, and you subtract the value of the oxygen 18 to 16 ratio in some standard that everybody agrees upon. Subtract those two, and then divide it again by the value of that same standard. Finally, you multiply that whole value by 1,000. So that's sort of the reason for this goofy percent symbol here, right? It's a percent symbol with an extra zero added on, because instead of doing times 100 like you would do to calculate the percent, like for a score on an exam or something, we're using 1,000. Okay, so again, it's the oxygen 18 to 16 ratio that's measured in some sample. In this case, it's going to be a foram shell, subtracted from the oxygen 18 to 16 ratio in a standard, divided by that same value of the standard, and all of that multiplied by 1,000. The reason that scientists use this notation is one, because the ratio of oxygen 18 to 16 in all sorts of things in nature changes only very, very slightly. So almost all of the oxygen on Earth is oxygen 16, and only a very small amount of it is oxygen 18. So these changes in the oxygen isotope ratio between samples and standards are always very small. That's why we multiply them by 1,000. The other reason is that mass spectrometers, the instruments that scientists use to measure these isotopes, are much better at measuring ratios than they are measuring specific quantities of single things. That's just the way the instruments work, and so because they're better at it, we have arranged our science to sort of allow us to be the most precise with our measurements. To illustrate this idea that the changes between oxygen 18 to 16 isotope ratios are very small, let's just do a simple sort of experiment with this formula here. Let's imagine that the oxygen 18 to 16 isotope ratio, let's imagine that the oxygen 18 to 16 isotope ratio of our standard is equal to 1. Just keep things simple. And then, so 1.0. And then imagine that the oxygen 18 to 16 isotope ratio that we measured in a foram is equal to 1.001. 1 and 1/1000th. Okay, so to go through our exercise here, we have the measured isotope ratio 1.001 minus 1 divided by 1. Okay, so 1.001 minus 1, well, that equals 0.001. 0.001 divided by 1 is equal to 0.001. Now, 0.001 times 1,000, That's a piece of cake. We just move our decimal point over 3 places. So a 1/1000th change in the oxygen 18 to 16 isotope ratio of some sample compared to a standard would equal a delta 18O value of 1. So you can see that very small changes end up becoming sort of easily palatable numbers like 1 or 2 or 3 when we use this delta 18O notation. It makes it much simpler for scientists to talk about the changes in isotope compositions. So if we come back to our figure here, again, now that we're familiar with this delta 18O notation, we can see that the 0 value here that's essentially the value of the standard that all of our scientists are agreeing on. And that value is changing in increments of 1, 2, 3, 4. So each one of these steps from 0 to 1, that indicates a 1/1000th change in the oxygen 18 to 16 isotope composition of these benthic forams compared to the standard, just like the example that we just did. So in this example, the oxygen isotope composition of our foram, or of our sample, was 1.001. It was 1/1000th greater than that of our standard. So that means that in this example, our foram has got more oxygen 18 compared to 16 than our standard does. And that results in a positive delta 18O value of 1. Let's do another example. This time have our forams 18 to 16 oxygen isotope composition be smaller than that of our standard. So if we imagine that the oxygen isotope composition of our foram is smaller, let's say it's 0.999 minus 1. We'll use the same standard value to keep things simple. 0.999 minus 1 is equal to negative 0.001. And now if we multiply that by 1,000, that gives us a value of negative 1. So this tells us that in samples with a lot of oxygen 18 compared to 16, right, a greater amount of oxygen 18, samples that have more oxygen 18 in them are going to tend to go towards positive delta 18O values. In contrast, for samples that have a smaller amount of oxygen 18 in them, right, so lower 18 to 16 values, those are going to tend to go towards, smaller or even negative numbers. It depends on the value of our standard. So we can think of delta 18O values that increase in size from 0 to 1 as becoming isotopically heavier, right? Because they're incorporating more oxygen 18, which is more massive, right? It's physically larger than oxygen 16 by 2 neutrons. So increasing delta 18O values we can think of as becoming heavier, and decreasing delta 18O values we can think of as becoming lighter, right? Because they have less oxygen 18 in them. So they are becoming isotopically lighter. So let's bring this back to our figure here, the oxygen isotope record of benthic foraminifera. Okay, so what we see is that through time, starting at about 50 million years ago, there's a general trend towards larger delta 18O values. So just note that the axis here has positive numbers going down, and here's -1. So -2 would be up here. That's just the axis has been flipped, showing positive numbers decreasing in this direction. Okay, so that tells us that from between about 50 million years ago to now, there's been an overall increase in the oxygen 18 to 16 isotope ratio in the shells of benthic foraminifera. But we'll also notice that there's sorts of like a lot of squiggles and changes in this isotope record, right? So what do these squiggles mean? What does this overall trend towards higher delta 18O values mean? How in the world is all of this telling us about Earth's climate? That's what we'll discuss next.